Hey everyone, welcome to The Explainer. Today we're taking a journey into the microscopic world of semiconductor manufacturing. It's really the hidden architecture that runs basically our entire modern lives. The device you're watching this on right now, the massive servers hosting the internet, the brains inside those sleek new electric vehicles, they're all powered by these unbelievably complex microscopic cities built on tiny wafers of silicon. So today we're going to break down exactly how human engineering manages to turn raw sand into literally the most advanced technology on the planet. Let's get into it. Tens of billions. I really want that number to just sink in for a second. We aren't talking about stars in a galaxy or, cells on the human body. We're talking about the number of microscopic transistors that can be packed onto a single fingernail-sized computer chip. It is an absolutely staggering engineering achievement. And understanding how we actually manage to put tens of billions of tiny switches onto a tiny square of silicon is exactly what we're unpacking today.
All right, really quick, here's our roadmap for this explainer. We're going to start with the brains of modern tech, zoom inside the transistor, and look at how these chips are printed. Then we'll bust the nanometer marketing myth, and finally wrap up with how modern 3D designs are basically outsmarting physics.
Okay, section 1, the brains of modern tech. Let's look at the journey from raw silicon to integrated circuits.
So the absolutely crucial point here is that chip fabrication is the bedrock of modern existence. Without this process, the technology we rely on, smartphones, AI systems, electric vehicles, life-saving medical devices, it simply wouldn't exist. This entire process happens in highly specialized, multi-billion-dollar factories known as fabs. Major players out there, guys like TSMC, Intel, and Samsung, operate these incredibly precise facilities. And their one job? To take pure, raw silicon and transform it into the integrated circuits that power our world.
Moving right along to section 2. Inside the transistor. This is the fundamental building block of all those devices. To really understand a chip, you have to understand its core component, right? The transistor. The most common type we use today is the MOSFET. Now I know, metal oxide semiconductor field effect transistor is a total mouthful, but honestly, just think of it as a microscopic on-off switch with 3 key parts. You've got the source, where the current enters, the drain, where it leaves, and the gate. The gate is the boss here. It sits right above a silicon channel and decides whether electricity is actually allowed to flow between the source and the drain.
And this right here perfectly illustrates why that tiny little switch matters so much. When the gate is off, no current flows. The computer registers a 0. When the gate is on, current flows, and the computer registers a 1. 0, 1, off, on. This incredibly simple physical flow of electricity at a microscopic level is the absolute foundation of all digital computing. Every text you send, every high-end video game, every massive AI algorithm, it all just boils down to billions of these little gates opening and closing billions of times a second. Crazy, right?
That brings us to section 3, how chips are printed. Because, we know what a transistor is, but how do we physically build billions of them at once? Well, the core technology behind the magic is photolithography. Obviously, you can't use a tiny pair of tweezers to place billions of transistors on a chip. Instead, you basically have to print them using light. The fab coats a silicon wafer with a light-sensitive chemical and then projects these incredibly intricate patterns onto it using extreme ultraviolet light. It's essentially like developing a microscopic photograph that physically etches a circuit board right onto the silicon.
Let's quickly walk through the full recipe step by step. First up, wafer preparation and oxidation. This is where pure silicon is sliced into thin disks and coated with a thin insulating layer. Second is that photolithography process we just talked about, projecting the blueprint. Third is etching, where the unwanted material is blasted away, leaving only our printed circuit pattern. Step 4 is doping. This is super cool. This is where specific impurities like phosphorus are blasted into the silicon to actually give it those conductive transistor properties. Step 5 is metallization, which adds tiny metal wires to connect all those billions of transistors together. And finally, step 6, the chips are tested, cut, and packaged. This entire cycle just repeats over and over, building up microscopic layers until the whole chip is complete.
All right, let's turn to section 4, the nanometer marketing myth. Time to decode what these buzzwords actually mean.
So if you follow tech at all, you've definitely heard these terms. Companies like Apple, Samsung, Intel, they're always bragging about their shiny new 5nm or 3nm chips. But let me ask you, what do those tiny measurements actually represent physically on the silicon? Are the transistors themselves literally 3nm wide?
Well, here's the plot twist you might not expect. These node names are not literal sizes anymore. Back in the early days of computing, a measurement like 5 nanometers roughly referred to the actual physical dimensions of a transistor's parts. But today, actually, scratch that, it's really just a marketing and generational label now. The physical dimensions of the components just don't perfectly map to these numbers anymore. But look, even though the nanometer number is more of a naming convention now, often called a process node, the benefits it represents are very real. Moving to a smaller node, say from 7 nanometers down to 3 nanometers, guarantees a specific triad of improvements. First, higher density, meaning you can pack tens of billions of transistors into the exact same physical space. Second, better performance, so the chip calculates much faster. And third, lower power consumption. And that right there is exactly why your phone battery lasts longer, even though your screen is brighter and your apps are way heavier. Finally, let's explore Section 5, Going 3D. This is all about how engineers are literally outsmarting the laws of quantum physics. So as these nodes kept shrinking, a massive problem emerged. Traditional flat transistors just stopped working well. Electricity would literally leak out because the components were just getting too impossibly small. The solution? Build upwards. First, we got FinFET, which became the standard in the 7 and 5 nanometer eras. Here, the silicon channel is shaped like a vertical fin, and the gate wraps around 3 sides of it to tightly control the electricity. But for the bleeding edge, we're talking 3 nanometers and beyond, engineers invented the GAA FET. Here, the gate completely surrounds the channel on all 4 sides. It is an absolute masterpiece of supreme efficiency at a microscopic scale. And honestly, this brilliantly illustrates why chip fabrication is arguably the most difficult thing human beings do. Just think about the scale here for a second. The features being carved into this silicon are thinner than a single strand of human DNA. We're operating at a scale so impossibly small that the normal laws of classical physics start breaking down. Quantum effects, like electrons magically teleporting across barriers, start to literally interfere with the electronics. To combat this, fabs have to rely on extreme ultraviolet lithography machines. These are hands down some of the most complex, expensive pieces of equipment ever designed by humanity. Ultimately, what you're really looking at when you hold a modern computer chip isn't just a generic electronic part. It is the absolute pinnacle of human collaboration. It's this perfect, incredibly delicate mix of theoretical physics, advanced chemistry, cutting-edge materials science, and mechanical engineering. It is a true modern marvel, and it's happening billions of times a second right there in your pocket. Which leaves us with this final kind of provocative thought. We've gone from flat designs to 3D fins to completely surrounded gates, shrinking closer and closer to the absolute size of a single atom. The pace of innovation has been totally relentless, but physics has hard limits. So what happens to our technology, to our AI, to our daily lives, when we finally reach the point where we simply can't shrink these transistors any further? It's a fascinating question, and one the brightest minds in the world are desperately trying to answer right now. Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.